Squamish, British Columbia, located 45 minutes north of Vancouver, is known for several things, most notably outdoor recreation and awe-inspiring landscapes. This mountain town is nestled between sprawling mountains at the northern terminus of Howe Sound, the southernmost fjord in the northern hemisphere. Here, nature and recreation collide in a spectacular way, housing some of the world's best mountain biking trails. We will explore how the rich geologic history of the region provides the unique landscape on which these trails are sculpted. While satellite imagery is a familiar sight in this day and age, it does not show the full picture. Overlaying a geologic map, we can see a diverse array of different formations instead of muted grays and greens. Each bright color is a different rock type with its own history. Examining each of these clues, we can determine the origin of the landscapes around Squamish, and this film will assemble the geologic story of this land through landmarks visible on the surface. An injection of adrenaline and creativity to most, mountain bike trails offer unparalleled access to these landscapes, and it is through this enviable resource we will explore Squamish's unique geologic history. The two main riding areas, Diamond Head and Alice Lakes, differ both in the experiences they give riders, but also the terrain hidden below organic topsoil. Alice Lake, famous for rock slabs and old-school tech, sits on granitic bedrock, formed more than 100 million years ago deep within the Earth's crust. While both areas share some of this same ancient substrate, the Diamond Head area comprises a much more contemporary coalescence of volcanism and glaciation and is heavily influenced by collapse events more recently. The third area, Valley Cliff, shares geologic elements from the other two areas and will therefore not be explored in much detail. Here, we will use a few select trails to explore how and why the landscape on which Squamish's trails are built was formed. The diverse history can be grouped into 4 chapters: mountain building, glaciation, the interaction between volcanism and glacial ice, and the more contemporary collapse events. The construction of mountains occurs in 2 ways, either through tectonic uplift or volcanism. Often, as is the case in Squamish, both methods interact. The movement of tectonic plates occurs on the scale of hundreds of millions of years. The most relevant tectonic event to our story is the ongoing subduction of the oceanic Juan de Fuca plate beneath continental North America. Large tectonic forces drive the Juan de Fuca below the North American, forcing it into the Earth's mantle. At depths of over 50 kilometers below the surface, the Juan de Fuca plate hydrates the mantle, causing low-density magma to buoyantly rise into the Earth's crust. The resulting intrusions of magma, known as dikes, are driven upward by hydraulic pressure, forming sprawling chambers of molten rock called plutons. When magma is driven all the way to the surface, it erupts to form a volcano. Dike systems are not permanent structures and shift constantly, although over the timescale of thousands of years. Once a pluton is cut off from a feeder dike, it begins to cool. At depths of 15 to 30 kilometers below the surface, magma cools slowly enough to form crystalline rocks, and given the chemical composition in the Squamish area, it forms granodiorite. Meanwhile, the subduction of the Juan de Fuca plate distorts the North American plate, pushing it upwards and vertically extending mountains on the surface. In southwestern British Columbia, this uplift causes mountains to grow about 2 millimeters a year. 2 millimeters a year doesn't sound like a lot, but occurring over the last 10 million years, a relatively short period of time geologically, this provides a staggering 20 kilometers of uplift. Obviously, the mountains here are not 20 kilometers tall, as erosive forces combat this uplift. Through this process, material once buried deep inside the Earth's crust is brought to the surface. In this way, granitic plutons formed 15 kilometers inside the Earth underpin the majority of the local landscapes we see today. On our map, granodiorite is shown in pink, and the incredible trail builders who grace Squamish have creatively exploited outcrops of this crystalline rock to create trails such as Intestinal Fortitude, Bony Elbows, and Garanga in the Alice Lakes area. Granite offers an incredibly grippy riding surface, even during Squamish's frequent rain. Here, under a microscope, you can see the individual crystals that provide the sharp edges that create friction. The textures at this micro scale interact with bike tires, offering an unparalleled amount of control. This allows for exposure, tight corners, and steep grades that would be impossible to ride on another surface. While the pluton that forms the base of these trails was created over 100 million years ago, its surface was sculpted much more recently. Chapter 2. Glaciation. Over the past 2 million years, ice sheets have swept over North America. During the last glacial maximum, around 10 to 20,000 years ago, the Cordilleran ice sheet sat 2 kilometers thick over Squamish. This is visible in the mountains today. Looking at the Garibaldi-Atwell complex, we can see that only the summit illustrates sharp angles, while the ridges leading up to it are much more subdued and rounded. This pattern is also visible when looking at Haybrick and Skypilot. This is because only the tops of the peaks were above the Cordilleran ice sheet. All terrain below approximately 2,000 meters in elevation has been carved and rounded by glaciers, resulting in the rolling nature and smooth U-shaped valleys below the summits. On the rock slabs of today's trails, we see evidence of this glaciation. Here, we see parallel scars carved into the granite by a glacier, and here the surface is polished almost entirely smooth. On a larger scale, horizontal striations are visible on this cliff, and these show the horizontal direction of the glacier's movement. Glaciation not only sculpted today's rock slabs, but also provided the material for the ground beneath many of Squamish's iconic trails. Glacial till is the debris removed from plutons and other large rock outcrops, and today covers most of the Diamond Head riding area. This material is visible on our geologic map in shades of green. It ranges in size from sandy gravel to car-sized boulders. This material was broken off of peaks and cliffs thousands of meters higher up and transported by the glaciers tens of kilometers down the slopes where they are deposited today. This material forms the ground below trails like Angry Midget and Pseudosuga in the Diamond Head riding area. As glacial till ranges from sandy gravel to boulders, the trails built on it range greatly in nature. Some, such as Pseudo, are generally very smooth, with the occasional gravel patch or low difficulty rock garden. On the other hand, Angry Midget features large boulders that a rider must either vault over or avoid. Chapter 3. Glaciovolcanism. Over the same time period as glaciation, the effects of volcanism are also evident on the trails we ride today. The northern half of the Alice Lakes trail system represents an area where volcanic material and a glacier collided. In this case, pyroclastic flows erupted near the summit of Mount Garibaldi. Pyroclastic flows are a mixture of volcanic gases, ash, and rock that can move downhill at over 100 kilometers an hour. This is the same type of event that famously destroyed Pompeii in Italy. Shown as the red area on the geologic map, pyroclastic flows thundering down the valley contacted the thick valley glacier that was still melting after the peak of the last ice age. This is evident by the rocks found today on the sides of trails. Here, next to the slippery salmon trail, this boulder is one of many examples. Looking closely at its structure, we can see much smaller crystalline structures than in the granodiorite we examined earlier. Additionally, it is porous, having visible air pockets within it. This means that this rock cooled very quickly while exposed to air. Found on the side of Craig's Connector, this boulder displays radial jointing around its perimeter. This delicate structure would not have survived the journey from the mountains down into the valley. Jointing occurs perpendicular to a rock's cooling surface, and since this boulder exhibits radial jointing, it must have cooled from all sides simultaneously. This would occur when hot material from an eruption collided with a glacier or other ice mass. Therefore, we can determine that the rock was not fully solidified when it arrived here and cooled due to contact with the Valley Glacier. In the Alice Lake Trail System, glaciovolcanic material forms trails such as Slippery Salmon, Robson Cliffs Corners, and Pamplemousse. In most cases, these rocks are boulders on the side of the trail, as glaciovolcanic material does not form the large rock outcrops that granodiorite does. Ash and other material from the pyroclastic flows more commonly forms the riding surface of a trail, but with a little creativity, even the boulders can be incorporated into a line. Chapter 4: Collapse. As the Cordilleran ice sheet receded around 10,000 years ago, the resulting floods blanketed material across the valley. These deposits form recognizable features on today's trails, as well as forming the current sand and gravel mines in town. On our geologic map, these deposits are shown in shades of orange and yellow. In this road cut that connects the Diamond Head and Valley Cliff riding areas, we see the glaciofluvial deposits exposed. On the surface, there is a thin layer of organic material, and then looking downward, we are effectively traveling back through time. This erratic collection of debris, ranging from silt to boulders, presents a tumultuous formation. Cycles of high and low energy depositional environments are illustrated by the jumbled layers of material. Periods of flood flows are shown by the presence of boulders, as the energy required to transport rocks of this size is very high. Layers of silts and sand represent low energy depositional environments. As water levels varied both seasonally, as they do currently, and over longer time periods during the melting of the Cordilleran ice sheet, this deposit and others were formed. Today, this glaciofluvial material provides the ground on which trails such as roller coaster, lumberjacks, and hoods in the woods sit. A glaciofluvial trail surface can range from smooth, flowing corners to awkward rock gardens and back again in a matter of meters. Another dramatic collapse event in Squamish's history was the creation of the Checkeye Fan, a feature on which much of Brackendale and its associated multi-use trail network sit. Seen on the geologic map in yellow, this alluvial fan is formed of over 1.6 square kilometers of material from up the Checkeye drainage. Essentially 1/4 of Mount Garibaldi collapsed into the valley and was washed down the drainage as seen in this 3D render. This is just one of many collapse events that have shaped Squamish, although it is certainly the most spectacular in its scale. So, in conclusion, we can categorize Squamish's geologic formation into 4 steps: mountain building, glaciation, volcanism, and collapse. Mountain building is a result of tectonic uplift and plate subduction, as well as the formation of granitic plutons. Glaciation sculpted the landscape on the surface, and the glacial maximums are visible in the mountains today. The interaction of volcanism and glacial ice produced smaller features visible on the surface, and more recently, collapse-type events have become the most prominent geomorphic force in Squamish. Looking ahead, collapse events will continue to dominate geomorphically, especially as anthropogenic forces increase in influence. On smaller scales, land development for residential, economic, and recreational uses, and on larger scales, climate change will destabilize delicate alpine hydrologic systems and influence collapse events in the future.